In this video series, I'll talk about how we can assess if a distribution fits your data. So let's say you gathered some responses, maybe 20 students, filled in a questionnaire, and you have their scores, and you want to know, okay, do their scores follow approximately a normal distribution, which is this bell shape? That is something that's useful to know because that's a main assumption that we often make, that scores are normally distributed, or actually that residuals are normally distributed, but we'll talk about that later in the course. There are some ways that we can assess if a distribution actually fits the data. We can make some plots, and we can even do a significance test. Previously, we talked about two different types of probability distributions. We had an empirical distribution, and this just describes the data. So for example, a histogram might describe how many responses were there in a certain area. In this case, most responses were here, which might be between like 5 and 6, for example, or whatever the scale is here. And we have the theoretical distribution, which is some form of mathematical formula, which is actually quite complicated and not something I'll talk about, but some form of mathematical formula that describes the probability of each possible outcome. For example, this bell shape for the normal distribution, which describes roughly how high a bar would be in a histogram if we would make it around this area. For example, here or here, in case the normal distribution holds. Now, if you remember the Galton board, which I have here, this is the Galton board, right? We had all these balls, and if I flip it, the balls will fall on these pins. Once. Every time a ball falls, it falls on the pin. It goes left or right with the same probability. 50% probability left, 50% probability right. You can think of this as throwing a coin, right? If it's heads, it goes left. If it's tails, it goes right. Then it falls on another pin, and the same thing happens, the same thing happens, and the same thing happens, etc. So this happens, let me quickly see, 14 times. And because of that, the final result is that the ball falls into one of these 15 buckets. The 15, the first one is labeled 0, which means that you never went right, basically. The last one is labeled 14, which means you went right 14 times. And then we have everything in between as well. The middle one here is labeled 7. That's the middle one, and you see it's the most likely to fall in here. Now, a nice thing about the Galton board is that the shape is actually approximately normal. You can see here, we have this approximate normal bell shape. That's actually a very interesting thing. The reason for that is the central limit theorem, which I'll come back at. So the true theoretical distribution is actually not a normal distribution. It's what we call a binomial distribution. A binomial distribution, and you don't have to really remember that. It's not part of this course other than mentioning it here and there. It's not something you have to remember really. But a binomial distribution is a distribution we use if we have multiple events that can have, for example, correct or incorrect, or heads or tails, or left or right. And if you take the sum of that. In this case, the ball can go left or right 14 times, which leads to a binomial distribution. Now, binomial distribution is a bit bell-shaped, actually, but it is only for for full numbers. So in this case, there's no bucket 1.5 or bucket 2.5 or bucket 2.6 or 2.7, right? There's nothing in between these buckets. There's just bucket 0, 1, 2, 3, 4, 5, 6, 7. Nothing in between. And because of that, we need to use actually a special distribution because the event is discrete, or the variable is discrete. Now, due to the central limit theorem, a normal distribution actually does hold well here, and that's very interesting. You see here that this bell shape does approximate the histogram here that we get. That's because of the central limit theorem. The central limit theorem is a very advanced mathematical theorem that states that if we take the sum or the average of independent events, things that are not influencing each other, in this case, going left to right here, does not influence it will go left to right on the second pin. In that case, eventually, if we do that a million times, actually like an infinite number of times, we will get a normal distribution, which is interesting. In this case, we don't do it infinite times, we only do it 14 times. So it's not actually normal. You see, we only have several categories, for example. But it should hold approximately well. We even know what the mean and the standard deviation should be from this distribution. And that's pretty cool. We normally don't know this, right? We normally don't know the mean or the standard deviation, the true mean or standard deviation. We can only estimate it from the data, but we don't know the population values. And we like to know the population values. So that's why we do statistical inference. We don't know them, but in this case, we do because we actually understand how this works. Now, the mean is 7, which is the middle bucket. That's pretty straightforward. The standard deviation is 1.87. That's very not straightforward. It actually requires some advanced mathematics, which I won't talk about in this course. If you're really interested in this, you can let me know. I actually have a YouTube video explaining this type of mathematics for a postgraduate course that I teach as well. But yeah, that goes beyond this course to really explain how you could calculate this true standard deviation. Now, we know that the central limit, due to the central limit theorem, the normal distribution should hold approximately well. But can we also test this? Can we test if we get a normally distributed set of responses? Right, so here I have the Galton board. Right, so the ball falls here, it goes left or right. It falls on the next layer, it goes left or right. Ooh, that's terribly drawn arrow, left or right, etc., etc., etc. It lands in one of these buckets, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And we see that most actually land on this average of 7. The true distribution is this binomial distribution, which means that if you would do this with an infinite number of balls, like a lot of them, we should get this shape. This one. We're going to approximate it with this normal distribution. Now, why is this an approximation? You see here, for example, that in bucket 4, the line is not a flat level, like here. But that doesn't make sense because we don't actually have 4.6 or 4.2. Right? It doesn't make sense that this is a different shape. Still, this bell shape approximates it pretty well. So we're going to check actually if this is the case. Now let's say I flip it once, and let's say I have 600 balls. I think actually there's 6,000 balls there, but let's say I have 600, and I get this sample. So I get, well, you can count them. I'm not going to do that now, but there's a large number of balls in 7, only 3 in bucket 2, and 1 in bucket 13. Now this data I'll put online, so you can play with it yourself as well in JASP. Okay, so here we are in JASP, and this is the data. These are all the balls. Basically 600 observations, should be 600, and the bucket it lands on. Now we can calculate some things. We can calculate the mean, for example, and the standard deviation. We go to descriptives. We drag this sample variable to the variables. And we already get this information here. We get a mean of, well, 7 in this case. That's very nice. That's exactly where we want it to be. And a standard deviation of 1.839, which is also very close to where we want it to be. That's nice. Well, we would expect, of course, that with a large sample size like this, the mean and the standard deviation will be approximately accurate. And this is based on theory, but it's nice to see. Of course, 1.83 is not 1.87, which is what standard deviation should be, but that makes sense. It's still a sample. Now, how can we look at if this data are actually normally distributed? Well, the main thing it will do is we'll make some diagnostic plots. And we can do 4 types, and I'll talk about each of them, how they work, and what you can find. The most straightforward thing is simply to look at the empirical and the theoretical distribution, which we call a PDF, a probability density function. It's a fancy name, but you might encounter it sometimes, so that's why I wanted to include it. Basically, this means we look at the histogram and we look at the bell shape of the normal distribution. Okay, let's look at that in JASP. So let's go to distributions. And if you don't have that, there's plus, right? You get distributions here. We go to distributions and we select normal. Now we want to define our distribution here. This stands for mean and variance. Remember the square here, the variance. We want to select standard deviation instead. We have standard deviation. So the mean is 7. And the standard deviation is 1.87. 1.87 is based on this theoretical standard deviation that I know. Normally, we do not know this. Okay, now this looks a bit weird, but we know that the range actually goes from 0 to 14. That looks much better. And now we could actually ask our things, JASP things, right? We can ask, for example, what's the probability to score below 7.5? We won't do that now, but this is what we use also to get probabilities. Okay, we can go to assess fit, actually first generate and display data. We could use this to draw new samples, which is nice. We're not going to do that now. We go to drag sample to get variable from dataset. And now JASP will look at this particular variable that we had called sample. So we had 600 of them. The mean is 7, the variance is 3, and the standard deviation is 2. And there's some other values here as well. Right? Now you can press some plots here. Histogram versus theoretical PDF, probability density function. And we get here this plot. Well, this looks a bit weird because the histogram is actually based on full numbers, integers, but it's trying to do it a bit different. We can make a separate histogram. We know actually should have 14 bins, or 15 bins, but it still does something weird. We can't actually get that shape correct in JASP because it shouldn't. It's trying to treat it as continuous, but it shouldn't. Anyway, we get this shape here. It's hard to really compare these because there are a lot of values in this bar, but it's not really fully accurate here because we can't set this bin width correct in this case. In this case, here we want to see, okay, it both looks bell shape, it both looks fine, but it's hard to really judge and compare this in JASP itself. If we do want to get a better histogram, we can go to descriptives, get statistics, sample, put in variables, basic plot, distribution plot. Then we get a much nicer histogram than what we have in the distribution panes. But here we can't really overlay it. We can just look, okay, it looks somewhat bell-shaped. A second thing that we can do is we can compare the empirical and theoretical cumulative density function. Cumulative means that we describe the probability of a value being less than a certain value. Basically adding everything up until some value. We can see it as summing all the bars in the histogram to the left of a point. If we go here, the cumulative distribution would be this one plus that one plus that one, that's 4. And at 5 would add the height of this one, at 6 would add that one, etc. These shapes should match, and these are a little bit easier to compare than these bell shapes. Let's look at that in JASP again. Let's go back to our results from the distribution pane. Right? We can actually remove these script statistics that I did. And this is what we get when we go to distributions normal. Now we can add empirical versus theoretical CDF. we add this, and we get this plot. Now this is a bit more interpretable. What can we see here? We can see two shapes. The smooth one, which is from the theoretical distribution, and the stepwise one, which is from the empirical distribution. Now this tells me it goes in these steps because it has only a certain numbers it can take, right? It can only take 2 or 3 or 4 or 5. And this tells me in the sample there are, what would this be, 10% maybe? 10% of the values are 4 or lower. For 6 it would be about 45% maybe. 45% are 4 or lower. 7 is above 50%. So 7 or lower, that should be more than 50% because 7 is the average here. That's how we can read of this plot here. Basically at these points we can look. And it goes like this because, yeah, these are all basically, there is a lot between 6 and 7. That's why we have these steps here. Now we see here that these are about the same. They look very close, which is nice, and which tells us that, okay, these look pretty similar. Now there are two other types of plots that we can make to see if the empirical distribution is matching the theoretical distribution. It is not always very easy to see this from the histograms or from the cumulative distributions. And for this reason, these plots are pretty useful, and they're often reported, especially the QQ plot is often reported, which looks a bit like this crying face with 2 tears, but it's actually a very nice plot. So, the QQ plot is a plot that matches quantiles of one distribution to another distribution. A quantile means a certain value of the distribution. So what the QQ plot does is it matches the values that we get in the sample. So just on one axis we put the values that we get in the sample. It matches that to the values that we should have gotten if the distribution was correct. And that we get through something we call a quantile. Now how does this work? It's pretty straightforward. We just order all the observations. We have the first, the second, the third, first, fourth, etc. Right? And let's say the first observation, let's say we have a range here from, let's say, 1 to 10. And let's say the first observation was somewhere here, like maybe a 1.2 or so, 1.3, something like that. And all our other observations are here in this range. Okay. Then if you would fit a normal distribution, we probably get something like this, right? So the bell shape mostly here. And this would be something we wouldn't really expect. According to the normal distribution, we would find a very low probability to get this value. The normal distribution tells us where should we expect our observations to occur. And if we say, okay, give us 100 observations from the normal distribution, for example, if you have 100 samples, we can use the normal distribution also to say, okay, where should we find these 100 observations? Where do we expect to find them? Maybe the first one we expect to find more like here, for example. Right. And this is a difference, and that's exactly what we're looking at in this QQ plot. How do we get it? Basically, for every point in the sample, we look how many observations are below that point. So let's say for this one here, we see there's one below. If you don't include this one, right, there's one below. And let's say if we have 100 observations, that means that there's a 1% chance of getting this score or lower according to the sample distribution. Now that 1% probability we can use to find which value belongs to a 1% left tilt probability, maybe here for example, in this normal distribution. And then we find the quantile like that, basically asking the distribution not for a given point what's the probability, but rather given a certain probability, what point should I be looking at? And that's actually pretty similar to what you might have already done if you look for critical boundaries, for example, in a sampling distribution. We basically look for the quantile that corresponds to a 5% probability. It's the same, roughly the same idea. The main thing you should take away is that the QQ plot allows us to see, okay, what are the values that I got in my sample, and what should they have been if the normal distribution or any distribution we're fitting was the correct one. The second plot that we're looking at is the PP plot. This is less commonly reported, but it's something we can get from JASP, so I wanted to show it as well. It looks actually pretty similar, except that here we're not looking at the values, but we're looking at the implied probabilities. So basically for every point in the distribution, you look at, okay, how many observations in the sample distribution were below it. That's an empirical probability. And for the theoretical distribution, we look, okay, what is the area of the theoretical distribution that is below that point? That's the theoretical distribution. And we simply draw those 2 points together. So basically in the PP plot, we're looking at the difference between the cumulative distribution for one compared to the other. If I go to this area here, for example, so for 0.5, we might be looking at, okay, so I have an empirical distribution this much. If I add all these bars together, then divide them by the total amount of observations, that's what I should get. This is actually the theoretical, this one here. How many balls do we have here divided by 600? That's the empirical probability. And then we compare that. So this is empirical. We compare that to the theoretical, or this one actually is also correct, but now we do it for normal distribution. We compare it to, let's say I had 5, right? So to this area here. Okay. The number of balls here compared to the total number of balls gives the empirical cumulative distribution. The area here compared to the total area gives me the theoretical cumulative distribution. And we basically compare these two together. These should match if the distributions are aligned, which is what we have here, right? They're very similar, but they might not match. And then we see, okay, where is the empirical distribution implying a different probability than the theoretical distribution is, and where is it not matching? For both these plots, they look very similar. We basically should see all the points on a straight line. We should see that the samples in the QQ plot and the quantiles from the theoretical distribution, or the implied probabilities, should be the same. If they're not the same, it means that the distribution is not the same and it's doing something different. Like it's implying something different, either according to what the sample should be or what the probability should be. Basically for both of these, we want the values to be on a straight line. So here we are in JASP again. We have our histogram versus theoretical probability distribution. This looked a bit weird here, right? Because we don't actually have continuous data. We have the empirical versus theoretical cumulative distribution, which is basically just this one, but then for each point summing the area to the left, which looks very similar. We have the steps in the empirical one simply because we have discrete data, right? And we're trying to fit a continuous data distribution, the normal one. So now let's go and enable the QQ plot and the PP plot. We can add confidence intervals if we want, but I will not do that now. Because you get this range, but I'll skip this for now. So you see for both, they're very similar. We see that the points are placed a bit weirdly, here horizontal, here vertical lines. That's because we have lots of values in the data that are the same. Like the balls just fall into bin 1 or 2 or 3, right? They don't fall into bin 2.5 or 2.6. So that's why we have this shape. That's okay. We basically want to see that these points fall roughly on this line, which is what's happening here. We don't really see any strong deviation from the line here. So in the QQ plot, here we see the sample values, right? So we have only 2 or 3 or 4. That's why the lines are horizontal here. And here we see their theoretical quantiles according to the normal distribution. What happened here is literally we just sorted them from the first to the last. This is the first one. This is the last one. And then we ask the normal distribution, okay, so this one has nothing before, or let's say 1 point. So it's either this point and nothing else. This has 1 point before it, so it has 2 points out of 10, 2%, 2 out of 600 I mean, sorry, 3 out of 600, etc. And we ask what are the corresponding quantiles according to the normal distribution, which means what are the values that according to the normal distribution should give this left-tailed probability of 1 over 600, 2 over 600, 3 over 600, etc. And then we plot those here. We see that here the values we get in the sample and the values we should be getting if the normal distribution is correct are roughly the same. They are not that different. We get this line here because we sort them. You get like 3 times the 2, but the algorithm still will compute a different probability for them. It's a bit weird, but that's what's happening here. In the PP plot, you see that now the scales are between 0 and 1 and not on the scale of the data, right? Because this is about the implied probabilities. Here we're looking at for each data point, what's the implied probability of scoring that value or lower according to the sample, which is just 1 over 600, 2 over 600, 3 over 600, 4 over 600, etc. Actually, I think 601, there's a small adjustment there, but that's really a minor detail. And what should these left-tailed probabilities be according to the theoretical distribution? If the normal distribution holds, what should be the left-tailed probability? So for each point here, what's the area under this curve left of it? Basically, what this plot is doing is just comparing the height of these two lines with each other. And you can see it as this plot, but then stretched out, where the theoretical distribution is stretched out to a line. Again, we don't see anything happening here. This looks very good. All the points are roughly on the line. We don't see them deviating from the line in some sort of systematic way. So this again looks good and looks normal. The final thing I want to talk about in this video is that instead of looking at plots, we can also use significance tests to see if distribution holds in the data. There are 2 tests we can use, actually more, but I'll just talk about 2. The Kolmogorov-Smirnov test. This is a test we can use for a fully specified distribution, which means a distribution where we know the mean and the variance. Normally, we don't know that. We just want to check, does a normal distribution hold? But we don't know exactly which normal distribution. We don't know the exact mean and variance of the distribution on the test. In the case that we don't know the exact parameters, we can use something called the Shapiro-Wilk test for normality. Now the null hypothesis is that the data are drawn from a specified distribution, which means that we do not want to reject the null hypothesis. We do want to get a p-value of larger than 0.05. That sounds weird, but basically, if we get a p-value, if we cannot reject the null hypothesis, then that's a good thing, because we want to try to reject if the normal distribution holds. If we cannot reject that, then that's good, because we get some evidence that the normal distribution might hold. Now that's nice, but a downside is that these tests are very sensitive to sample size. Like the normal distribution will never really be correct, or any distribution will never really be correct. So it tends to be significant for very small deviations. And that makes these tests a bit less useful. So the diagnostic plots are much more informative. You often get a significant effect here. It doesn't say much. If I want to show them, you'll see them often reported in literature, but yeah, they're hard to interpret, these significance tests. It's not necessarily the case that a significant effect means that you cannot assume normality holds. It might be a very small violation. So let's look in JASP again. And we see here that we have also the statistics here. And we can do some tests. There are multiple. We're just going to use Kolmogorov-Smirnov. In this case, because we actually know the distribution. We know it should be a mean of 7 and a standard deviation of 1.87. But we'll also do the Shapiro-Wilk in case we did not know that. And we just want to see if the best possible normal distribution holds. Alright. We just get some test statistics and a p-value. And what we can see here is that the p-value is very significant for both tests. That's striking because our data look bell-shaped. Our cumulative distribution is very similar. Our QQ plot showed that the quantiles are very similar. Our PP plot shows that the implied probabilities are very similar. So why are these significant? Well, again, these are not actually continuous variables. They are discrete, 7, 8, 9, or 10. That by definition already means the normal distribution is not exactly correct, but it can still be a pretty good approximation. So in this case, we'd say, okay, according to these plots, the data looks sufficiently normal, even though we reject the significance test. And that could be because we have a large sample, 600 balls. It could be that we have a large sample, that we just pick up these very small deviations from normality, which are small. And it means, yes, technically, normal distribution does not hold here. But in practice, it's still a very useful distribution to approximate this data based on these 4 plots. And that's it for this video.